Hello guys, welcome back to Maths on African Motives. We are still on our Electrotechnics N4, and this is going to be a full paper revision that we are going to consider, considering our August exams, which is the paper that we wrote on 26 July 2024. So as we are given that calculators may be used, and also you need to go through our instructions so that we do understand what is it that we are required to do. So our instructions and information, the major part there is supposed to read all questions carefully, answer all questions as usual. The number answers according to the numbering system used in this question paper. So make sure you do maintain that and start each question on a new page. All right, this is for you guys. And also the pen that you're supposed to use, blue or black. So we're given first question, principles of electricity. Various options are given as possible answers to the following questions. Choose the correct answer and write only the letter A to E next to the question number. All right. So we're given on the first part 1.11. How can change of flux be obtained? Is it by changing current in the circuit? Is it by adding more resistors? Is it by reducing voltage from the supply? Is it by changing the direction of the rotation of the magnetic, which is the rotation of a motor, or none of the above? If we are to consider flux, because, okay, resistors, we can't be talking of resistors, adding more resistors, guys, flux and resistors. We are talking of maybe current, this and that. That is current and what? That can be working with the resistors that we are not like resistors. Reducing the supply, that is a total no, because remember, our S is actually affecting in terms of the voltage. The more it is, actually, with the change of flux, there's no relationship. So there's no change that is going to happen there. The direction. So what about the changing of current? That is the one that we need there. By changing current in the circuit. Also, we can consider our flux. Also, remember this formula where we have got our flux being equal to IN over S. So meaning to say, as we consider our current is affecting directly to the flux. So the moment we change it, flux is also changed. If there was something about maybe number of turns, which we do not have, so meaning to say the first answer was going to be the best one, which is A. Then on 1.12, which of the following cannot strengthen the magnetic field in electromagnetism? Which one cannot? Okay. A, placing an iron core inside the solenoid. This one is going to strengthen. It is strengthening. Permeability. Does the permeability part increase? No, there's nothing there. So this is the one that we need. Remember, let's look into the current. Increasing the current, no. Increasing the number of turns, keeping the current constant. No. All of the above definitely is not going to work because permeability does not work with what? With strength. It cannot strengthen. All these, they can strengthen the magnetic field, but only permeability cannot. Remember this in your magnetic field, guys. Make sure that you also go through your theory. That can be easier because these questions, guys, they need you also to have like a basic of what you've been doing there. The magnitude of the hysteresis loss depends upon the following. Which one of these that the hysteresis depends on? Okay, A, the type of material used. Does hysteresis work with that? Truly, the type of material that is used is going to affect hysteresis. The heat treatment and mechanical handling to which the specimen has been subjected. Truly, it affects hysteresis. These two. Only A none of the above, A and B. So we're going to see that A and B are our answers there. So our answer was going to be E, where we're talking of A and B at the same time. These two answers, they do work. In what? They do work. They do work as the magnitude of hysteresis loss to depend upon. So meaning to say, your answer there was not going to be A only or B only, but both A and B was supposed to be our answers there in its description. Fleming's left hand rule for motors includes, in its description, what does it include? What does it talk about? The thumb, which is directional force, is part of our Fleming's left hand rule. The index finger, it's also part of it. The middle finger, direction of, it's also part of it. So meaning to say all of the above were going to be our answer. All these, they do work in the description of what? Of our Fleming's right hand rule. All right, this is the left hand, sorry. Working with the left hand. Then on this other part, which of the following is not included when describing Fleming's right hand rule for generators? Which of the following is not included of these? The left ear for listening. The ear. Guys, we're talking of the right hand rule and we're talking of the left ear. What does it have to do with the hand? So this is not part of our answer. The first finger, the thumb, the second finger, they're talking of that right hand. So this part is actually true. It's included, this part. Which one is not included? The left ear for listening. Do we need that? Do we need that, guys? No. We do not even need that. So that was the part which is not included. So also these questions, guys, you see these questions, you have to choose also the best answer that you're given there. What are two types of capacitors from this part? Air or mica type? These are types of capacitors. You do know this. Electrolytic type. It's also a type of a capacitor. It's also a type of a capacitor, that one. So C, they're saying A and B. All right, A and B, which is this one, A and B. So that is the true one. It can't be only A because B is also part of it. It can't be only B. So the answer was going to be A and B. These two types are these three. They're also type of what? Capacitors. Remember those paper capacitor? It depends with the type of the dielectric used there. Okay, 1.17. Ohm meter, whether solid, liquid, or gas, is made up of minute particles called, which can further be subdivided into atoms. All matter is made up of what? These minute particles are called, they are called molecules. These are called molecules. So meaning to say, of these answers, the best answer was going to be A, where we've got the molecules. Okay? The unit of in which a current of 1 ampere flowing for 1 second generates 1 joule of thermal energy is measured in ohm. And is measured in ohm. Which one? The unit of what? Can you say the unit of a resistor? No. We say the unit of resistance. A resistor is the component, but its unit, the unit of resistance, what it carries is the resistance, which is measured in ohm. You cannot, current is not measured in ohm, ampere, voltage. So that was going to be the best answer, which is B, not the unit of resistor. A resistor is a component, then its resistance is measured, its resistance. 1.19. If the thumb, index, and middle fingers are held at right angle to each other, with the index finger pointing in the direction of the flux and the middle finger in the direction of current. The thumb will indicate the direction of the force. All right, they are saying, okay, so it's like this description that we are given here is for what? That is the type of question that you're given then. Because if you check here, if what, then what is the question? They're just giving us answers. So from the answers, we can see, all right, it's the law or the rule that we are supposed to consider, which states this. Which rule states this? Talking about the middle finger are held right angles to each other with index finger pointing in the direction of flux. That is our Fleming's left hand rule, this one. Guys, if you've forgotten, remember the right hand rule, what you had before? Even if the guys here, if you've forgotten here, remember what you had here. Your Fleming's left hand rule. You're talking about a thumb, direction of force, index, finger, direction of flux, middle finger, direction of what? Of current. Isn't it that we're having there? The index point direction of what? Of the flux. The middle finger in the direction of the current. The thumb in the direction of what? Of the force. This is what we had exactly here. From what? Fleming's right hand rule. Left hand rule, I mean. The right hand now is talking about the flux. It's all about the flux, this and where we talk of first finger for magnetic flux, the thumb for direction of motion, the second finger for what? Direction of EMF. So you must know between the difference. And as we are doing revisions, guys, I just hope we must find time where we're going to talk also of these presenting in terms of the diagram. This is just an exam, hoping that you had learned this. But we're going to also try to have presentations which can differentiate a lot of things as we are revising. Then on 1.110, the direction of the induced EMF is always such that it tends to set up a current opposing the motion or the change of flux responsible for inducing that EMF. So which of these is describing that? Which of the law or the rules that talks of the direction of induced EMF always such that it tends to set up a current opposing the motion? You're talking of what? The Lenz's law. This is the one that we are going to consider there. So meaning to say, according to our answers, the best answer was going to be A. All right, we cannot talk of these, guys. So the best way, know your rules and your laws. By knowing them, even if you're given a definition, then you just, okay, this is the definition for this. Know your definitions. So the first 10 marks that you had, the first 10 questions that we had there needed us to work more with our theory. More with our theory. All right, considering 1.2, you were given that a bakery oven dissipates 170 megajoules of energy. So we were given, in this case, according to the information that we have, it dissipates this energy. So we are given the energy, which is, you can write as Q, and write as W. As long as you understand what you're writing, you can write as E. As long as you understand what does it mean. So you're given 100 megajoules. During every 5 hours of operation, every 5 hours, the time frame that was given in its operation to have this energy, it was every 5 hours. And if the oven is supplied at 230 volts, calculate 1.2, the resistance of the element. All right, you have voltage here, and they want you to calculate the resistance. If, let's say, I have voltage and current, I was going to work with this, then try to manipulate and make resistance the subject. I'm just going to divide by current like this. Resistance is equal to voltage over current. but I do not have current. So meaning to say, we can think of another formula. From where? Because we just have voltage there. The question was, what about what we are given from these two? These two, the energy and the time. What is it that we can have or obtain from there? And whatever that we can obtain from there, is it going to help us to find resistance? Remember, power can be obtained if we have energy, because we do understand that power is equivalent to the energy over the time taken, which is our time in what? In seconds. We have the power. And having the power resistance can be calculated because there's so many formulas that we have for power. Remember, power, we're talking of just a direct calculation of power. Power is equal to VI. So current can be calculated. Power is equal to I squared R like this. You can also try and see if current is there, but you can say current is not there. Also, power is equal to V squared over R. So guys, you can see that the last formula will be the best one because you just need power and voltage, which is voltage is already there in order for you to find what? Resistance. There, using the first formula, you have to calculate the current. After calculating the current, then you use the formula voltage is equal to what? IR. You must use a lot of stages if you are to use that. But if you are to use this one, you just need the power from there. So let's calculate our power first, as we can see that it is needed. So power is equal to what? The energy, 170 megajoules times 10 to the exponent of 6 over what? The time in seconds. This is 5 hours. But how many seconds do we have in 5 hours? Remember, an hour is equivalent to 3,600 seconds from your 60 times 60 multiplication. So meaning so you're going to have 3,600 an hour. But remember, there are 5 hours, so it's 5 times this to get the number of seconds. So that was going to give us the power, which is 9,444,444 like that in watts, which we can convert to kilowatts. If you want, you can just divide by 1,000, which will be 9,444 kilowatts. If you divide by 1,000, you have the power. And this power is the one that we needed to determine what? The resistance. So using that formula, guys, we're going to find your power, because there it is stating that power is equal to what? Power is equal to V squared over R. So if you're to use the first one, this first formula, you're going to calculate current. Then you use the formula for voltage is equal to IR like I mentioned before. But this one is direct because the power is there, voltage is there. We just need to find resistance. So let's make resistance the subject. We're going to cross multiply. RP is equal to 1 times V squared, which is V squared. Remember, you need resistance. So divide by the power, divide by the power. So meaning to say resistance was going to be equal to V squared over P. From that, resistance can be calculated. V squared, the voltage that you are given there. What is your voltage? 230 squared over the power that we calculated, which is 9,4. That was 9,444 kilowatts. So kilowatts, that simply means times 10 to the exponent of 3. So this is times 10 to the exponent of 3. That was going to give us the resistance value, which is 5,6012 3 decimal places. If you are using 3 decimal places, you can just fix your calculator to 3 decimal places. Then whatever that you're calculating will be to 3 decimal places. Remember that conversion of your calculator. So we could have obtained power, the resistance from there. So using the first one, I said you could have calculated current, then you use that. Guys, it's up to you. 1.22, they need you to determine or to calculate the cost. This time it is the cost to operate oven for a month. What is going to be the cost? Remember, whenever we talk of the cost, the first thing that we need to focus about is the kilowatt hour. The kilowatt hour is just like the unit cost. which will give us the unit cost from there. So it will give us the unit cost at the end. It gives us the unit cost, like per unit, meaning to say per each kilowatt, per each. That is the, so you're given that at a unit charge. I'm gonna talk about the time, but let's talk about this one because they are saying at a unit charge of 1.75 rand. This is the kilowatt hour that we are given. Like, how are we, like, per each kilowatt, per each kilowatt, per each kilowatt. That is what they mean there. All right. So that's 1.22. Let me try explain this. So that is saying per each 1 kilowatt hour, per each, it is going to be equivalent to 1.75 rand. This is the unit. Like each unit, a unit charge of. So as they are talking of the kilowatt hour, for us to obtain the total cost which was used, meaning to say we must find the total kilowatt hour that was used for that month. There is a need for us to determine the total kilowatt. So in order for you to have the total kilowatt, that's where we take our information now, because we need what? The total kilowatt hour. Total kilowatt hour. So we have to consider that. What is it? They are saying if the oven operates for 5 hours per day, it's going to be operating 5 hours. For how many days? For 25 days per month. Take note what they are saying here. It operates 5 hours in a day, each day. But in a month, per month, how many days of operation per month? Per month, 25 days were being used. Per month, 25 days were being used. So in 25 days, how many hours do we have? That is just like a simple proportion there. How many hours were being used? So you can have the total number of hours first. So the total hours is simply going to be 25 over 1 times 5. So that is simply 25 times 5. What is that we need? This is going to be more here. So it's 25 over 1, whatever that we get times what? Times a 5. We're going to have the total number of hours that operated, which is 125 hours of operation in a month. Take note, this is happening in a what? In a month. 125 hours. So total kilowatt is going to be what? When you talk of kilowatt hour, simply multiply the kilowatts times the number of hours. The power is simply power times time. Power times time. Remember, power is measured in what? Kilowatts. Time now is supposed to be in hours because you talk of kilowatt hour. So that is simply what you're talking about. It's simply power times time that gave us what? The kilowatt hour. So you have to take your power in kilowatts. Remember, you calculated the power in kilowatts of this same oven, because it's the same oven that we are talking about. And it has to use 9.44 kilowatts in every 5 hours of operation. 5 hours per day, 5 hours of. So we're not going to recalculate the power because we calculated this power during every 5 hours of operation. So it's a continuation. The power is already there in 5 hours. Remember, that's why you converted this to seconds. So this is the power that we have. So from this power, our kilowatt hour now. So our kilowatt hour is simply power times what? Time. But this time is supposed to be in hours. Power in what? In kilowatts for us to obtain kilowatt hour. So our power in kilowatts was what? Now we need that power. So remember, our power in kilowatt, that was 9.444 like that. The one that we obtained in kilowatts. Then we use the time in hours, which is the total time that we're going to talk about in this case. And what is the total number of hours? We obtained 125 hours. Time in hours. So kilowatt times hours will give us kilowatt hour. So this is the total kilowatt hour that you're going to have, which is 1,180.5 kilowatt hour. You can even just like kilowatt hour, or you can just like the way that you understand, you can write this way. This is our total kilowatt hour, the total for that month. For a month, for the whole month of operation, this is the total that was used. So meaning to say we now use that unit, which is per each, because we have the cost. So now to determine the cost, what are we going to do? Because we are given that per each kilowatt hour, we are going to use 1,75 Rand. What about for this total that we just calculated of 1,180.5 kilowatt hour? What will be the cost? The unit cost is from a kilowatt. So you measure or you compare it from there. Definitely this is going to be more. So that's this over 1 times 175. So therefore our cost was going to be 1,180.5 over this 1 times the cost now of 1,75. So this will give us the total cost. So remember, this was kilowatt hour. So definitely kilowatt hours is what? You've cancelled there. So you just remain with the total cost at the end. And this was going to give us 2,065, it was going to be 875 something, which is going to change this into 88. Remember, you're talking of the money where you're supposed to round to 2 decimal places. So that was going to be our total cost for that month. For a month, this was going to be the total cost. So the kilowatt hour, also try to recap with your engineering science N3. Those were your questions, guys, in your science N3. Remember, if you're dealing with electricity, you worked with that cost. So you can also try to recap using that. Study Fig 1 above. We are supposed to study this and use Norton's theorem to calculate the voltage drop across the 25 load resistor and draw equivalent circuit diagram. So they want us to calculate the voltage drop across the 25 ohm resistor. So in order for us to have the voltage drop, we must calculate first the current that is flowing from that using our Norton's theorem. So remember your Norton's theorem, just similar to your Thevenin in 102, but in terms of the Norton's theorem, what we are going to need, one, they said is study this diagram. So in our study, we can see that these two resistors, R1 and R2, are in series. So I can even combine this and make it to be a single resistor if I want. You can just save this so that my diagram does not look that complicated. All right. So you can even reduce this. All right. So that was 1.3. It's another, you can even use as they are, but you can even have your diagram like this with a single resistor. All right. Then we have got our voltage, which is E there. Then we're going to have our R3. All right. Then connected to R4 and RL. R4 and RL, they are also in series. But for us now to combine, because we are working with R4, remember, we're working with R load, the load resistor there. So in order for us, we could have combined this. I'm not saying it's wrong. You can do that, but they avoid, because that is where you need to calculate whatever that you're asked there. So just try to make it separate, even if it is a series. You can combine that. You can have that. I actually talked about this for those maybe who are watching this video and they're doing industrial electronics. I talked about this scenario where you can combine these two resistors. You can also choose to leave it like that. All right. So our R3 is going to remain as it is, 15 ohms. Remember, I combined these two resistors because there's nothing that we are calculating there. There is no load resistor. So We can even combine them. It's not a problem. So 10 plus 5 is going to be 15. Remember, we are in series. So this is a 15 ohm resistor. You can just write R series 1. Remember, this we got from the series combination. Then our E is given, or you can write as V, which is 60 volts. So using the Norton's theorem, remember the stages of your Norton's theorem. You can also consider the videos for industrial electronics and for I talked about Norton's theorem as an introduction. You need to calculate the short circuit current. But in order for you to calculate that short circuit current, which you can also refer as your Norton's current, it must be as a result where you short that resistor. Short the resistor RL. That's a short circuit. A short circuit is not open, but short, like it's supposed to be just closed. Like it's just supposed to be no resistor like that. So that is to short. So meaning to say from our diagram, the diagram was going to look like this. If we short that, we're going to have the first part. Remember, we combine these are now two resistors in one resistor. We're going to have our R form. We're going to have our R3 here. We're going to have our R4. But the part where we are supposed to have our A and B, remember A and B is supposed to be between the part where we are removing the load. But you're not removing it as in Thevenin. No, you are shorting. To short, that is to make a continue. It's just going to be like this. That's a short circuit. Remember, short circuit. It's just a straight line. So in no resistor, just be short circuit like that, which is between the points A and B. But as you can see, the short circuit that we have affected here is also affecting R4 because R4 is part of that current here. This is our R4, remember? This is our R4, which is 20 ohms. The current that is flowing across R4 is the same current that is the one that we want across the branch AB, which is the one that we are referring to as our short circuit current or our Norton's current. It is the one that we have there. It's the same current that is flowing here, same branch. It was the same branch. That's why I'm saying we could have even removed it. But for the sake of understanding our topic as a separate, but let's just work with RL removed. I mean, short-circuited, but R4 as it is. So meaning to say these are the resistors. They were going to remain as they are. Your R3 as it is, which is 15 ohms. Remember, we calculated this series combination. We got also 15 ohms, and this is our E, which is 60 volts. So how are you going to have the short circuit current? According to the look of the diagram, in order for you to calculate the short circuit current, you use whatever that you understand about this circuit, your Ohm's laws, the Ohm's current divider rule, everything that you do understand. So we can see that if, let's say, there was a current here, let's say there was a supply current which is following the total current. Let's say the total current is there. Were we not going to calculate this short circuit current or our Norton's current? It was going to be possible because these two resistors, they are going to just give us a voltage divider. It will be like this. This is the total current flowing. But what is happening with our total current? Another part of this is taken by R3. Another part of current is taken by R4, which is our short circuit current. So meaning to say current divider rule, there it plays a role. Make sure that you also go through industrial electronics. I mentioned or talked about the current divider rule as a subheading, as a subtopic on its own. It can help you to understand whatever that I'm trying to explain here. With your current divider rule, this is the current flow. You're not going to focus with what is here. You want to focus with the current that is being divided. This is the current divided into this resistor, another one into this resistor, another one into this resistor. So this one is the one that is in R4. This is our R3. In R4, that is where short circuit current is here. So meaning to say, in order for you to have that short circuit current using your current divider, what we're going to say? The short circuit current, which is our IN, was going to be taken from what? Current divider, you use the opposite. It is flowing in this resistor, the current that you want. But you use the opposite resistor on top for current divider rule, you use the opposite resistor on top. So it will be R3 over the sum of the resistors that are dividing that current. Remember, the current is divided into these two resistors. So you have their sum times the total current which is being supplied to those two resistors. So by having this total current, you can see that it was going to help us because these two, they are sharing that current. So we're simply going to use this approach. But how can we have that total current now? How? If we have total resistance, total current can be calculated was simply voltage over resistance. From the total voltage over the resistance. But we do not have that total resistance. So how are we going to have the total resistance? Guys, this is our circuit here, like we can see it. Here there's a supply. So meaning to say we consider to say the current flowing here, when it is branching in, remember the concept of your parallel. The current is flowing and it's when it meets, when at this junction, another one goes here, another one here. So it means R3 and R4, they are in what? Parallel. They are not having same current. The current is going to be subdivided, so they are in parallel. So meaning to say the total resistance was going to be taken from the one that we got in series plus R3 and R4 in what? In parallel. R3 parallel to R4. That was going to be the condition. Meaning to say we are simply talking about the series combination plus the product over sum. So that's the product R3 times R4 over the sum of R3 plus R4, which is in series. Remember, we combined that 10 and 5. We got a 15. You can even leave it as R1, R2. Then we add R1 plus R2. It's still one and the same. So this is 15 plus product over sum. The product of R3 and R4, 15 and 20. So we need the product of 15 and 20, also the sum of 15 and 20. So that was going to give us the total resistance of the circuit, which is 23.571 ohms. That's our total resistance, which is going to help us now to find the total current. From this, total current can be obtained. What is the voltage that you are given? That is 60 volts over what? The total resistance that you just calculated, which is 23.571. So the total current could have been calculated from there. And that was going to give us 2,546 amps. With this, we can now think of what? Finding now, determining of the short circuit current, because this is the total current that is flowing here, the one that we just calculated. This is the one that we calculate 2,546 amps. And from this idea that I was saying, it is being shared between these two resistors. These two resistors, they are going to share that current. Another one, it branches in R3. Another one, it is taken by R4. That one in R4, where our short circuit current is being presented, or our Norton's current is being presented, is going to be from our current divider rule, as I stated here. So that's R3 on top. What were the values there? Remember, R3 was 15 ohms and R4 was 20 ohms. So it's going to be R3, which is 15 over the sum, R3 plus R4. So that's 15 plus 20. Whatever that you're going to get here, you multiply to the total current, which is the one that we calculated there, of 2,4, 2,546 amps. So we are going to obtain our short circuit current or our Norton's current in that case, depending on the way that you're writing this. And that was going to give us 1,091 amperes as our short circuit current. So what is the purpose of the short circuit current? We are going to use it on the equivalent diagram. So, okay, let's just stop, guys. We've got your answers, because I'm just going to remove one or two here. So this is our short circuit current. As I said, we are going to need this one. So that was it, guys. You see now that all these, they are supposed to be shown, all these calculations, they are supposed to be shown. You're supposed to show all these calculations. So we calculated our short circuit current or our Norton's current. And from this, we got or we obtained 1,091 amperes. Let's see. Let's move on. What is it also that we need from our Norton's theorem? Just like in Thevenin's theorem, you are going to need what you call the look-in resistance, which is your Rn. So in that case, you need also to find or to calculate Rn, which is the same as how you calculated your Rthev when you're dealing with Thevenin. If you understand your Thevenin, how was it calculated? We have to remove all sources of EMF that you're given and replace them by their internal resistances. There's an EMF here, so we have to remove it, replace by the internal resistance. So meaning to say this diagram was going to be like this. You remove all sources of EMF. So we are going to remain with resistor, and there we're going to have our R3 going to R4. Remember, we now open that part of B, A to B. We no longer have a short circuit like what we had here. It's no longer a short circuit. This time, you just open those points, okay? The point of A and B, because you need to calculate, like I said, the look-in resistor is the look as you look into, like the way that you look into the diagram. How do you see these resistors connected? How do you see these resistors connected? Remember, this is our series combination that gave us 15 ohms. This was our R3, which gave us also, which was 15 ohms as we are given. This is the R4 that we had here, which was 20 ohms. So that is how it was going to look like. And you calculate your Rn here, which is the same as your Rthev. Remember, this is how you calculate your Rthev. Look in resistance. This is our look-in resistance. As we look into the diagram, how do we notice the arrangement of these resistors? As you can see, R4, if let's say a current was taken, how was it going to be? It was going to be subdivided into these two. So these two, they are in what? Parallel. In series with what? With R4. So meaning to say our Rn was going to be R4 plus these two, which are in parallel. So you have to consider our RS1 parallel to what? Parallel to R3. Remember, we combined those R1 and R2. They gave us a single resistor. This is our series combination that we obtained in parallel. So that is it. What is our R4? That is 20 plus parallel combination product over sum, as I explained before. So that was going to be 15 times 15, which is our product, over the sum 15 plus 15. So this was going to give us our Rn. That was going to give us Rn, which is 27.5 ohms. So with your Rn and the In that we calculated, our short circuit current, the current flowing across the load now can be calculated. But in order for us to understand this, you will need equivalent circuit diagram. So I'm going to take these values as they are. Do not forget your values, your Rn. So this is what we're going to have. We obtained these values. Okay, and also our Rn is given. We calculated this and got 27.5 ohms. The question truly, it was for us to calculate the voltage drop as we are given here across the 25 ohm load resistor. But in order for us to have that voltage, I said you need the current. So you need the current across the load. This is best understood if we have the equivalent circuit diagram. They're asking you to draw that equivalent circuit diagram later on, but it is best for you to have that equivalent circuit diagram of our Norton's theorem. Remember, our equivalent circuit diagram according to our Norton's theorem. We have got the current. So current, you can just put a circle and indicate with an arrow going up. You can also indicate this way. Still up to you the way that you understand. So there is our Norton's current, and we are going to have the Norton's resistance. So it will be a parallel like this. The Norton's resistance to the load resistor. So those are the points A and B, where the load resistor, the one that you actually ignored as you're working with your calculations. Now you have to put it back into the circuit. So our short circuit current, or our Norton's current, we calculated that was 1,091 amps. This is our Rn. As we calculated, we got 27.5 ohms. This is the load resistor, the part that AB is. That is the part where the load resistor was. There, A and B. So you take that load resistor. Remember, RL is 25 ohms. So that is the part of our RL here, which is what? 25 ohms. So the question is, we need to calculate the voltage drop here. You must have the voltage drop across the 25 ohm. So you can't have that without the current flowing across the load, which is our IL. We cannot have that. So in order to find this IL, using the equivalent circuit diagram of our Norton's theorem, how do you calculate IN? Remember again from our current divider rule again, because this is the current. Remember, this is current. This is the total current. It's flowing. How is it going to flow? At this point, at this junction, one of this is branched into this resistor. Another current is branched into this resistor. So as you can see, these two resistors, they are going to share this. It's now like our total current this time. So just like what we had previously, it means IL was going to be calculated using current divider rule. You use the opposite resistor on top, Rn. So the formula is Rn over the sum of the resistors. So it's Rn plus RL times the total current supplied to these two resistors. And our total current supplied is called what? IN, our Norton's current. So that was going to give us the load current. That's Rn, as we calculated, 27.5 over the sum. So that's 27.5 plus RL, which is 25. Whatever that you're going to have, you're going to multiply to the Norton's current, which is the one that you have, or your short circuit current, 1,0. That's 1,091 amperes. So this will give us the load current, the one that is on the load, and that was going to be 0.571 amperes. Is it what the question is about? No, the question wants the voltage drop across. Now the voltage drop there can be calculated because we have got the current. So what was going to be there for our voltage drop? Remember, the voltage drop, current times what? Resistance. So which current are we talking about from this voltage drop across the load? We are talking about the load current. Which resistance are we talking about? We talk of the load resistance. So the load current we calculated, that's 0.571 times the load resistance, which was 25. That was the condition of our question now. You had to calculate the voltage drop, and the voltage drop was going to be given as 14.275. So this was going to be 14.275 volts. Just like that. That is the voltage drop now across what? Across the load resistor. That was our question. Answer the question, guys. The voltage drop here. That was our question. Calculate the voltage and draw the equivalent. So already we have drawn our equivalent. So if you are to have this as a separate answer, you're just going to present your equivalency. This is the one that we have already drawn there, our equivalent circuit diagram. So that's what you needed. You can combine these with other calculation that I removed so that it can make sense. So Norton's theorem, like I said, just go through also the revisions for N4, industrial electronics. There I explained these theorems, like every theorem that is required in our syllabus, 1-1. So it can help you to just have the basics. DC machines on question 2.1. Fig 2 below is a construction of a DC machine armature assembly. Give the correct name for each labeled part and write only the name of the part next to the letter. Considering A, what is it that we have back there? This is our shaft. So these diagrams, guys, know your diagrams, revise your diagrams as much as we can. B, remember that's our cooling fan here. So you talk of the cooling fan, then C, which is on this part. On top there is the armature core. Then D is the armature windings. Sorry, D here, the winding. This part of G, there is the armature conductors. It's only guys, but you're supposed to have like on top, then you have the armature conductors inside for that is J. So I'm gonna also try to have a picture quality, the one that has got like the color so that you can also see this. But I hope from your textbooks you've seen this diagram. So C is your armature core. That was your armature core. D was going to be the armature windings. These are the armature windings. Then considering E, that is the part of the commutator. This one, it's our commutator. Then F at the end there, these are the bearings. We talk of the bearing. And G, this is the armature conductors, as I said before. So we've got our armature conductors. So just go through, and it was 7 marks, guys, just to fill in. You see, it was actually like a competition with calculations because this was just to name. Okay, anyways, it can happen like that, guys, in exam. You must expect questions like that in your revision. Do not neglect those theory and those diagrams. They do also work. On another part of our question, which was 2.2, they gave us the flux density in a pole, in the pole course of 8-pole machine. Of 8-pole machine, meaning say the number of pair poles. If there are 8 poles, so how many pairs? Divide by 2, so we've got 4 pairs. So P, remember, number of pair poles, is 1,4 Webers per square meter. They're simply talking of the Tesla there. That is magnetic flux density. So they gave us magnetic flux density, 1,4 Webers per square meter. The cores are 60 centimeters in diameter. So we're given the diameter, 60 centimeters. As we need area, square meters, divide this by 100 to convert to meters. It was going to be 0.6 meters. Remember, a meter is equivalent to 100 centimeters. So you have to divide by 100 there. And we are given the leak coefficient is 1,2. So the leak coefficient is given 1,2. There are 650 conductors, Z, number of armature conductors that you are given. That was 650 conductors, which is lap wound. Lap wound. C is equal to what? 2P. So meaning to say our C was going to be 2 times P, the number of pair poles. So C was going to be 8. Lap wound. Remember, it can be wave, where C is just equivalent to 2. There is 2P. That is equivalent to 2P in that case because of what? Lap wound. The machine is running at a 350 revs per minute. Speed, revs per minute. And what else do you calculate? The generated EMF, which is E, the generated EMF. With this information that we are given, guys, the only formula that we can think about is just a DC machine. You don't even know it's a motor, it's a generator, it's just a DC machine. The generated EMF, we use the basic one, which is equivalent, remember, 2P times your magnetic flux there, times the number of conductors that we have, the speed. If it is given with the 60C like this, the division of 60 here tells us that this speed is supposed to be in revs per what? Per minute, because of the 60. If 60 is not given in the denominator, therefore you're supposed to use revs per second, but there 60 is there on my formula. So I'm going to use this in revs per minute. So I have the purpose, but I do not have the magnetic flux. I have this, I have this, I have this. So where am I going to have the magnetic flux? We are given, remember the flux density is equivalent to flux over area. So flux is going to be what? It's going to be the flux density times the area. But because of the leak that we are given, because we are told that there is a leak of 1,2, this flux is going to be the flux density over the leak times the area. So remember this area, we are talking of what? Where we are given the diameter. So we're simply going to use pi d squared over 4 for area. So the flux was going to be calculated, guys. The magnetic flux was going to be magnetic flux density 1,4 over the leak coefficient 1,2 times the area. As I said, pi d squared over 4. This is the part of what? Your area. So the diameter is there. So it was going to be pi times d squared, 0,6 squared over 4 times the area. So from there, you were going to obtain the magnetic flux. And that was going to be 0,32986, which is simply 0,323 Webers. Like I said, you can fix your calculator, guys, to 3 decimal places so that you do not have a problem. It was going to be 0,33 like this, guys. This is 9. All right, it was 86 like this. All right, so it was going to be 33 because this one is going to change. Remember, to 3 decimal place, 1, 2, 3. This one was going to change into a 10 and it gives a 1. So it's going to be 33. It's going to be 330 there, which is just 33 Webers to 3 decimal places. If you fix your calculator, it's going to give you direct, okay? If you fix your calculator, guys, it's just going to give you that answer with a 0 there. So with this, we can now substitute because we now have the flux. E can be calculated just like that. This was a direct question. So that's 2 times the pair poles. How many pair poles? P, remember we said 4. That is for the flux. We just calculated our magnetic flux 0,33. All right, so this we got 0,33 times Z, number of armature conductors, which is 650, times N, our speed, revs per minute, which is 350. Everything over 60C, everything 60 times C. For being a lap wound, we got 8 as our C. So meaning to say the generated EMF was going to be calculated, and that was going to give us 1,251,25 volts. All right, so that was the idea. So this question, I think the disturbance was on the leak coefficient. We have to include that in the calculation of what? The magnetic flux. The leak has to be there. And with this, the magnetic flux can be calculated and substitute into the equation that we have that is giving us the EMF or the voltage generated. A long shunt compound generator. Compound generator. We are talking of a generator there. A long shunt. Remember, the shunt field coils are connected across the series field and the armature when it is considered like that. So they are taking, you take this and calculate find the terminal voltage. Let's just save a diagram. Remember, there's a long shunt. So a long shunt generator, we're going to have the shunt field like this. The part of the series field here, the part of the series field is the one that is connected. The shunt field are connected across, okay, coils. The series, and they're like, this shunt is connected across the series and armature together. So you're going to have the series here. The series field and also the part of what? Our armature. This is the presentation of a long shunt generator under compound wound. So this is our series field And this is part of our armature where we're going to talk of Pn, the power that is input. As we do understand, this is where the generated EMF is going to talk of the armature resistance. As we do understand, in a series combination like this, the armature current that is flowing here is the same as the series field current that we're going to have there. These two, they're the same, flowing in the same branch. So it's the same current that is flowing here. Remember, it's a generator which has to supply the current there as the load has to be supplied. Another current going into the shunt field, okay, where we have got our shunt field, and in this case, having our terminal voltage and P out, just like that. So they gave us, with this understanding, we can actually answer this question because they gave us that it supplies a load current of 65 amps. The load current here is 65 amps. Let us just try also have our information aside. So the load current is given, which is 65 amps, and has an armature resistance of, we are given armature resistance there, which is 0.1 ohms armature resistance, and the series field resistance of 0.25 ohms. That is our series field resistance, with a shunt field resistance of, we are also given that of the shunt, which is 55 ohms. The generated EMF is 248. The generated, they gave us what was generated. Find the terminal voltage, which is V. This is what we had. Remember, on a long shunt generator, referring to the EMF, we, depending also with your textbook that you're using, if they wrote in terms of the EMF or they wrote in terms of V. But in terms of the generated EMF, we do understand this is equivalent to V plus whatever that we are going to have as we are to consider other resistances, like voltages. The voltage drop, that is for the armature, and that for the series field. Remember, we have to consider adding the part of the armature. So the part of the armature here is, it consists of what? It consists of the armature resistance, but also there's a series field. So the series field has to be added with its series current. But we do understand this is the same. This here is the same. Like I said before, that is the armature current and the series field are the same. So instead, we can have this as IA in place of the series field. You can even factor out IA if you want. You understand that one, you can even factor it out. It is up to you, or you can just substitute here. So in this calculation, we do want to calculate the voltage. So definitely in your own understanding, you go, okay, I need voltage. So let me just make voltage, not E, but voltage, because the one that I want is voltage. So you're going to make your voltage the subject E. You take this to the other side, it becomes a negative. This to the other side, it becomes a negative. You're making it the subject. So it was going to be minus armature current, armature resistance, minus armature current, series field is equal to V. So this is the formula definitely that you're going to say, okay, this is my right formula to calculate what? To calculate my terminal voltage. You can even factor out the armature current, like I said, it's fine. With this formula now, you're going now to try to figure out what is that you are given, because you need to calculate the terminal voltage. Now you figure out what is it that I'm given. I have E, all right? Do I have the armature current? No, you're not given that. Armature current is not given, which is the same armature current that we need here. Armature resistance, as we can see, is there. The series field is also there. It is the armature current, which is not there. And we have to find this from our series field, from our combination that we have of the compound wound long shunt generator. We do understand that the armature current, which is our series field, is the one that is supplying. So it is the sum of the shunt and the load. It is one that is supplying, remember. It is one that is supplying. Another current flows here. Another current goes to the what? To the load. So from that understanding, we do understand that armature current is the sum of the load current and that of the shunt field. We have that one of the load, which is 65. But we do not have for the shunt. So we're now forced to calculate for the shunt again. what is our current in the shunt? In the shunt, we take the voltage V, the terminal voltage V, to be the voltage that is affecting here, direct at the shunt. Direct there, the shunt. So with that understanding, I shunt, it's V over R shunt. Okay? You remember your formulas also, guys. That is V over R shunt. Do we have this? This is the one that we need. So it was going to be a confusion to say, they want me to calculate V. But I am having a formula again, which consists of that V that I'm supposed to calculate. So let me just leave it like that and have it in terms of that V. Because remember, V is supposed to be calculated. So it can be an advantage for us to leave it in terms of V. So we do not know the value of V because it is supposed to be calculated. But the shunt resistance we are given. What is our shunt? That is 55. So meaning to say this is the presentation of the shunt current. If the shunt current is or can be presented this way as V over 55, therefore the armature current can be written in terms of V also, because armature current is equal to the load current, which we are given 65 amps, plus what? The shunt current, which is the shunt current is the one that we calculate in terms of V. So there we are forced now to leave our answer in terms of V. So it's going to be V over what? 55. We have an expression which represents the armature current. It's an expression, 65 plus this. So with this expression, we can now take it into the substitution, depending with how you wrote your expression here. If you factored out armature current, you substitute as it is with that one factored out. It's up to you. If you want to maintain like this, the way that I'm maintaining, it's also up to you. Just going to substitute. Remember, V is the one that you need to calculate. So there's no substitute for that V. E, we have it. That is 248 minus the armature current, which is this expression that we got here. But you're supposed to multiply to the armature resistance. So you can start by the armature resistance because it's just a single value there. It's just a single value. Take it, 0,1. Armature resistance, 0,1 into your armature current. So it's like armature current times, we have this first resistance. So I just started with the resistance. Guys, remember product of A and B is same as BA. So it does not matter which one you start with. Then you can now substitute your armature current, which is 65 plus V over 55. This is your armature current. Minus the armature current again times the series field resistance. What is our series field? Let's start with that one. Series field, 0,025. So 0,025 into what? The armature current, which is 65 plus V over 55, if you want to have it that way. You could have factored out armature current, like I said. If you understand it that way, please use it like that. So as we can see, we have formed an equation where V is, and we can solve for that V. There's a V to be calculated. There's also a V to be calculated on this part. We have a V. There's also a V to be calculated here. So that's an equation which we can now solve. All right, so V is equal to what? Let's solve, guys. That's 248. Expand the bracket. Minus 0,1 expands everything. So it's just going to be like this. You multiply here. That was going to be minus 0,1 times 65. You're multiplying. So it was going to give us minus 6,5 on that one. So it was going to be negative 6,5. You multiply minus 0,1 to this. Here it's 1 over 55. So it's minus 0,1 times 1 over 55. This is how you're supposed to have it. So it was going to give us a decimal negative 0,00182. But take note, there is what? There is a V there. So you put a V. Same thing, multiply, expand your brackets here, minus 0, this times 65. It was going to give us a negative there. All right, so it's going to be negative 0,000455. I'm just going to use like 3 important digits if there are too many zeros like that. You do the same thing, the minus 0,125, it multiplies here, just like what we had to do. It's minus 0,025 times what? This is 1 over 55. So you have to multiply to 1 over 55 like that with a V. So it was going to be negative. That was going to be negative. All right, the first one. So this one is the one that I multiply with this one, guys. Yeah, let's correct this one. The first one, this one, and this 65 was the one that was going to give us a direct value, negative 1,625. Here I'm working with a lot of things. Okay. Then the minus 0,25 multiplying this 1 over 55, this one, is the one that was going to give us that decimal of negative 0,000455 with what? With a V. So be careful there. Also your calculators, how to use your calculators. So as you can see, just like the previous case, we have our V. We also have the part where V is. We also have the part where V is. So these are just like terms that you need to collect to one equation. This is same like there's a 1. So we take this to the other side, it becomes a plus. We take this to the other side there, it becomes a plus there where it is. Or you can even avoid that and work with the left-hand side. I mean, the right-hand side first, simplify there if you want to avoid those confusions. Okay, let's just work with that way. Because someone might say, okay, this is a lot. Let me just first simplify the right-hand side, which is fine. So on the right-hand side, what is that you're supposed to simplify there? The numbers first. There's 248 here, minus 6,5. These are just numbers where V is not there. There is minus 1,625, this one. So you have to combine these. And you combine the part where V is, this part here, we have got V. And also here, we have got our V. So you're going to combine these and see what you're going to have. All right, so let's combine the numbers 248 minus 6,5 minus 1,625 was going to give us 239,875. The part where V is here, the part where V is, as you can see, this is minus 0,0182, minus 0,0, whatever that we have there. It was going to give us minus 0,002275 V. So remember there's a V there. Then now you can take the V to the other side of the equation. On this other side, it will be a plus. This is a 1. So the moment you take this to the other side, it becomes a plus there. It will be 1,002275 V, which is equal to this 239,875. Remember, you want to calculate the value of V. So what are you going to do? Definitely divide by this. 2275. Divide by that 1,002275. By doing this, you are going to obtain your terminal voltage, which is our V, and that was going to be 239,33052, whatever that you have. So it's going to be 331 there. So it's 239,331 volts. The terminal voltage. So they tried by all means to play us around there. To play us, they tried to make you understand. Do you understand the topic, or you just peruse through? If you are perusing through, this type of a question was going to give you a challenge. Understand the topic, the concept of the topic. If you understand the concept of the topic, you're not gonna have any problem. So, like I said before, we are going to work on that, guys. Introductions, where we left in terms of the introductions. We can also list that on the comment section. Remember, your comment section, guys, is there for you. Let me know which part that we actually have to work on as we are to talk of these presentations, our classes. We have topics that need to be polished up. Let me know about that so that we can polish those topics as we are revising together. So having a continuation, we can see that on question 3, which is part of your AC theory, 3.1. Name 5 detrimental effects of a poor power factor. When a power factor is considered to be poor, what is it that it is going to cause? What are the effects that it causes? So we talk of the consumption of power. It costs consumers more for the same load. The load that was supposed to be taken at a good power factor, it will be costing more. So we're gonna consider that it costs. So this one is gonna cost consumers. That's consumers more for the same load. The same load that was supposed to be at a cheaper price, now it will be expensive for consumers if the power factor is poor. Thicker cables have to be used in that case. You must consider thicker cables are to be used. You have to consider the use of the thicker cables. The increase in the copper loss. There is also an increase in the copper loss. So that is the increase in I squared R losses. All right. It limits the output of both generator and transformers, meaning to say output is limited. So limits the output. So that is the output of both generators. That is considering the generators and the transformers at the same time. So you're supposed to consider that. And also machines become less efficient. Machines become less efficient. So if you have got any other, depending with your textbook, let us know, guys. You can even add for others in the comment section so that they can also use those ones, such as supply of power. I can even add those ones, the supply cables overheat, supply cables, they also overheat because of that poor power factor. Overcurrent occurs in a second. There are so many. Overcurrent occurs in a circuit. So like I said, if you have got any other, please just let us know, guys. Let us add those ones that we actually do have. It can help someone in understanding these theoretical questions. 3.2, the following information about a circuit is known, Z1 and Z2. Determine the following. 3.21, the sum of Z1 and Z2. That's Z1 plus Z2, the sum. And convert your answer into polar form. After determining that sum, do not forget to convert your answer to polar form. Remember, Z1 is there. That is 5 plus J9. What are we adding? We are adding Z2, Z1 plus Z2. Z2 is given there. This is minus 8 minus J12, like this. So you're simply going to add. Remember, addition, expand. It's just like it's a plus 1. So there's no effect. It was just going to remain as 5 plus J9 plus and the minus, that's minus 8 plus and minus, that's minus J12 is just a minus. Then you're going to consider the real terms on their own, 5 on it, and this negative 8, meaning to say combining these two, 5 minus 8 was going to give us a negative 3. Then the part where the J is 9 minus 12. 9 minus 12, that's a minus 3. So that's minus J3. We got our answer in what? In a rectangular form. But they want this answer to be converted to polar form. So are we going to use those mathematical skills in conversion? No, they want us to just simply use our calculator in doing so. Remember your conversion to polar form, that's shift. You press the plus where the pole there is going to show polar form. This is minus 3. So the first one is minus 3. You separate the minus 3 on J, shift close bracket so that you separate that. So now you can have your minus 3. Close the bracket is equal to. So as you know, in polar form, it's R angle of theta. So it's going to give us the value of R. That's 4,243. This one is going to round off to 3. And the angle is also given theta minus 135. So that was 4,243. And the angle was minus 135 degrees. So that is the sum of these two, Z1 and Z2. In what? Polar form. In polar form. So if you add Z1 and Z2, it will give you answer in ohms. Okay, remember Z1 and Z2, there's nothing that you have affected. So the answer is just going to remain in ohms like that. So Z1 plus Z2, we got our answer in polar form. Just in any case, we might need these answers. Also, remember your answer in what? In rectangular form. But as you can see, these answers is just polar form, polar form, polar form. So it's best that we keep the one in polar form. 3.22 Z1 minus Z2. Z1 minus, it's a subtraction now. Just going to take your Z1, 5 plus J, 9 as it is, all right? The first one, there's no need for you to put the bracket because it's on its own, guys. The second one is going to be affected, especially when there's a minus like this, you can see it. This is minus 8, minus J12. I want you to see what's going to happen there. There's a minus, so the minus affects everything. So it's 5 plus J9. The minus affects, so it's minus, minus. That was going to be a positive 8. Minus and a minus here is going to be a plus J12. So as you can see, the minus, here's the power. It affects. With that, you have to consider your real terms on their own, the imaginary terms on their own. So 5 plus 8 was going to give us 13, 9 and 12 was going to give us a plus J21, which is in rectangular form. So in polar form, just like I use the calculator there, guys, you're going to get to 24,698 at an angle of 58,241. So use the calculator the same way that I presented there. So that was your Z1 minus Z2. There's no way that Z1 and Z2 here is needed. We can even erase this one. Okay, that was our answer there. And Z1 and Z2, you can even write the ohm. The ohm is still there. Z1 times Z2 in polar form. Okay, by first converting Z1 and Z2 into their polar form. So they want this Z1 to be in polar form. Remember, Z1 is 5 plus J9. It's just like the way that we converted that minus 3, minus this one, the same way that we converted that. Use your calculator, convert your Z1. So your Z1 was going to be given as 10,296, the angle. You are going to get 60, the theta there. That's your angle. It was going to be 60,945 degrees. You do the same thing for this Z2, which is minus 8 minus J12. Use your calculator. You're going to get 14,422 at an angle of minus 123.69 degrees. That is your Z2 and your Z1. And they need the product by first converting there. That's 3.23. So now determine Z1 and Z2, the product of Z1 and Z2. Remember, in polar form, how do you multiply? You're given your Z1, 10,296 at an angle of 60,945 degrees. You multiply this to Z2, which is 14,422 at an angle of what? At an angle of minus 123.69 degrees. So this was going to give us the product. Remember, in polar form, R1 multiplies R2. The angles, you add theta 1 and theta 2 from Z1 and Z2. So you're going to multiply your R1 and your R2 together. You multiply these numbers. So if you multiply those numbers, you're going to get 148,489. The angle now, you add theta 1, theta 2. This is our theta 1. This is our theta 2. We add. So it was supposed to be 60,945 plus minus. Okay, there's a minus 123 there, minus 123.69. You're supposed to do it. So plus and minus is going to give you a minus, definitely, guys. So it's 60 this minus this. And the answer was going to give you minus there. All right, that is going to be minus 62. It was going to be minus 62,745 degrees. And we cannot say ohm here because, guys, there's a product. This is Z1 in ohms. You multiply to another Z1 in ohms. So it's going to be ohm times ohm, which is ohm squared. So don't write the units for this one. Just leave it like that. The product of Z1 and Z2 does not mean that our answer is in ohms. No, that one, it will be wrong if we say so. Same as division, because if you divide Z1 and Z2, you are dividing ohm and ohm. So you cannot say your answer is in ohms. Your answer is just write your answer for these ones. They just, even there, that's why they even do not write like ohm or just write your answers. No problem. Just like that. You have to convert first. 3.22 Z1 divided to Z2 and leave your answer in polar form again. Z1 by Z2. You're dividing this time. Z1 over Z2. So already the advantage is that we have already converted these to polar form. Remember, division is best in polar form. Z1 and Z2, they are there already in polar form. 10,296 at an angle of 60. That's 60,945 degrees. What about Z2? We have it. That's 14,422 at an angle of minus 123.69 degrees. Division, how do we go about it? You divide your modulus R1, R2. The argument to subtract theta 1 minus theta 2, the angles. So you're going to subtract this. But these ones you have to divide as they are. Divide these numbers, these two. You have to divide as they are. That's your R1 divided by R2. So that was going to give us 0,714 at an angle you subtract. So as you're subtracting is 60,945 minus, because that one is carrying what? A negative. 123.69 degrees. So the minus and minus will become a positive. So you're adding this time. So it was going to give us 184.635 degrees. So like I say, this is in ohms. This is in ohms. If you cancel, so you cannot write any. Just leave it like that. You do not know the units. We cannot say ohm there. No. If it is just like Z1 and Z2 plus and minus, because you're subtracting, it's like you're subtracting 10 ohms minus 6 ohms. The ohm will remain there. It will be just 4 ohm. But not to say it's 10 ohms times 10 ohms. It cannot remain as an ohm, but we have to consider that to say the ohm there. But guys, this exam, you can even just write the way that, and they will mark these guys, you know them. 3.25. 13 times Z2. The product of 13 and Z2. We remember this is our Z2 here. So let me just answer it here where we can see our Z2. Remember our product here. We talked about this. Let me just not remove this. So that's 3.25. 13 times Z2. 13 is just a normal number. Z2 is a number that is in polar form. So how can we have this in polar form? The 13 in polar form is 13. What is the angle? The angle is just a 0. So that's 13 at an angle of 0 times Z2. Remember, our Z2 is already in polar form. That was 14,422 at an angle of minus 123. So that is the concept when you are given a number, just a number there. You know that the angle is what? Is a 0. So we talked about the product R1 and R2. So that is this one and this one, 13 and 14,422. You multiply these two. So if you multiply these two, you're going to obtain 187,486. And the angles, remember, theta 1 and theta 2, you have to add. So you have to add these to 0 plus minus this. It was just going to remain as a minus 123.69. There's no effect. There you can write an ohm. There is no problem because the number multiplying to an ohm, so it can even remain with an ohm. What about the next one? 3.265 over Z1. It's a division. So Z1, remember, we have it. So I'm just going to write where we have our Z1 here. We need a division this time. 5 over Z1. All right, so that's our 3.26. 5 over Z1. So 5 again is just a whole number. How can we have this in polar form at an angle of 0? So that's 5 at an angle of 0 degrees over Z1. Already it is in polar form. That's why we have to convert this to polar form. That was 10,296 at an angle of what? 60,945. Remember our concept of division as we used it before. Divide your R1. Okay, I remove that one. Divide your R1 and R2 together, these two. For the angles, you subtract. For the angles, you're going to subtract theta 1 minus theta 2, 0 minus 60,945 for the angle. But these, you divide as they are. 5 divided to 10,296 was going to give us 0,486 at an angle 0 minus this. It was going to be minus 60,945. So that's it. Dividing a number. This is just a number. Like it's just a number. It's not like any resist. It's just a normal number. So you can even write, but you cannot even write ohm because it's like 1 over ohm. 1 over ohm is not ohms. So they do not write the units if you do not know them. Just leave it like that. Because it's going to be 1 over ohm, which is not an ohm. 1 over ohm. A number divided like 1 over an ohm. We cannot say our answer is ohms also. No. That would be wrong to write it that way. So that is it, guys. Let's have 3.27. If, all right, we have to calculate x. If x is equal to the product of these, but express your answer in rectangular form, your answer. Z1 by Z2 over Z1 plus Z2. Remember your concept of parallel, but they gave us the Z1 and Z2. Remember we calculated this. Let's just have it here and see what are they trying to say. All right, no problem. Sorry, I need Z1 and Z2, the product. It's this one. I need this one first. I need this one. I need this one. And also Z1 plus Z2 is there. All right, so these two, I need them, guys. Let me just have it here. So this is our question, guys. That is 3.27. Find x if x is the product. Z1 times Z2 over Z1 plus Z2. As we calculated, because these are there, remember, your item, this one. So it means if this is wrong, you're going to have this question being wrong. If also 3.21 is wrong, your answers, remember, guys, you lose a lot of marks. So you are taking from 3.23, remember Z1 times Z2, this one, we calculated it here. It was 148,489. At which angle? At an angle of minus 62,745 degrees. Remember, division is best to be done in polar form. Then you can convert your answer. Z1 plus Z2, remember, Z1 plus Z2, we calculated this in polar form, which was the first question. The first question, this one. We got our Z1, this one. So you're going to write 4.243 at an angle of minus 135. So we have Z1 and Z2 also in polar form. We calculated this, okay? Remember, what was our answer there? It was 4,243 at an angle of minus 135 degrees. So this is where you are. As you can see, we are just back to your division in polar form, where the numbers have to be divided on their own. The angles have to be subtracted, as we have been using this before. So if you had to divide these two numbers, you are going to get 34.996. Then the angles you're going to subtract. That's negative 62,745. On your calculator, you subtract. What are you subtracting? Minus 135 degrees. Your calculator knows all these calculators. Do not worry about it. It will simplify this for you. You're going to get 72.255 degrees. This is what is our x is representing. But this x that we are talking about, it is in what? It is in a polar form, as we can see. But they are saying the x to be calculated there in its final presentation, let it be in what? Let it be in a rectangular form. So the x that we calculated here, you are supposed now to convert it to rectangular form. So therefore, our x was going to be what? To rectangular form, our calculator. All right, let me talk about this one because the last time that I showed you it was conversion to polar form. Just you've forgotten how to convert to rectangular form. This is what you need. Shift to rectangular form, you press a minus where the rec is here there. So it has already opened the bracket for you. So that's 34. We need 34 as it is, comma, 996. So to separate it to this one, you have to separate with this one, to put that one. How do you separate? It does not change. Shift, close bracket. As you can see, it gives us a comma. You see the difference there? This one is like a dot. This one is a comma. This one is a dot. This one is... So now you can put that value as it is, 72.255. You close the bracket. What is the answer in rectangular form, where we expect to have our x in the form of, as it is given, it will be x plus or minus j, y like this. So they will give you the value of x and the value of y. So these are the ones that you're given, the x, 10,666, like that. And what is the value of y? It's a positive 33.33. This one is going to change into a 1. So you'll be given x and y there. So your x, 10,666 like that, plus j, the part of y now. The y, as I said, this is 33.33. This is going to change into 1. So that's 33.331. So this is what they wanted you to simplify as, like your answer to be converted to rectangular form. In rectangular form, at the end, let your answer be in rectangular form. So as you can see, our AC was done. Our AC theory, they wanted us to understand the complex. This one, it was, we can just say, let's say they asked you a mathematical question. It was your maths N4, this one. They just brought you back to your maths N4. These questions can be asked in maths N4. They just brought you back to your maths N4. Do you know that? That is what they are trying to ask you. We do not have like the AC that we know. We have complex numbers there. So it can be like that. Transformers on question number 4.1. Name 4 functions of oil. Name 4 functions of oil used in an oil-cooled transformer. What are the functions as we are to use the oil in an oil-cooled transformer? What are the purposes? It serves as a coolant. The oil that is there, it is a coolant. So it serves as a coolant. All right, that's part you're supposed to have it. Also, it prevents easing, which is eking actually. Prevents eking. So it prevents eking. Okay. Then also it serves as a secondary insulation. It can also be used as a secondary insulation. So it serves as a secondary insulation. As a secondary insulation. Also, it can act as a barrier between the paper insulation and the atmospheric oxygen. So it also acts. It acts as a barrier boundary. That is, there's nothing like between, as a barrier between. There's supposed to be between two things for us to have a barrier between what? Between the paper insulation and the atmospheric oxygen. The atmospheric oxygen. All right, so with this, guys, we're going to have 4 marks. So any other part, let us know, guys, on the comment section, so that anyone that wills to that is willing to learn can learn from your information there. It's another learning platform to share your information there, because we are learning, guys. 4.2, a single phase. We are in a single phase, 480 over. So we are given, according to our information, that is 480 of 48 over 480 is like we're given V1 and the voltage. If you're given a transformer, these are voltages, primary, secondary. 48 over what? 480 volts. Then we are given that it's a 50 hertz transformer. The frequency of the transformer is given as 50 hertz. Here's a net area of 10 square centimeters. Area in square meters. How do you convert square centimeters to square meters? You multiply by what? 10 to the exponent of -4. If it was square millimeters, how do you convert to square meters? You multiply by 10 to the exponent of -6. Your answer will be converted to square meters from square millimeters. These are square centimeters. And a maximum flux density, not flux, but a maximum flux density, 1,8 Tesla. Estimate the number of turns in each winding that we have, talking of N1 and talking of N2. Estimate. How are you going to have this? The moment you're given this maximum flux density, you think of the EMF equation, where we talk of the maximum flux there, because remember the maximum flux there is used. From where? From the maximum flux density. From the maximum flux density, remember flux density is what? Flux over area. So you're just going to cross multiply. So that is the flux density times area. So the maximum flux density that we had there and this will give us the maximum flux. What is our maximum flux density? 1.8 times the area in square meters. So you're going to obtain the maximum flux there, which is something like 0,0018 Webers. Why are we determining this? We do understand in our transformers that if maximum flux is considered, then the EMF has to be considered. Remember that E is equal to what? We're also given this from our formula sheet, 4,44 times frequency times the maximum flux times what? N, the number of turns. So meaning to say, if I consider the primary side, I'm going to use E1, here I'm going to use N1. If I consider the secondary side, I'm going to use E2, here I'm going to use N2. That is what it means. So you can calculate the number of turns because E is going to be taken as our V1. So E is there, frequency is there, maximum flux, we have it. We just need N, which is the number of turns. So according to this formula, N1 was going to be what you divide by this. So it was going to be given as E1 over 4,44 times frequency times the maximum flux. Let's substitute E1 as our voltage given there. That is 48 over what? 4,44 times the frequency. Remember, we are given frequency that is 50 hertz. The maximum flux, as we calculated it, it was 0,0018. So that's it. We have got the number of turns on the primary side. So this is what we are going to have at the end. That was going to be 120,12, something like that, 120,122, which is going to just write as a whole number. So we've got 120 turns on the primary side. You can use the transformer ratio, which is fine, or you can even still use that to find N2 because it's the same equation that you have to just change. If it was 2, if it was 1, then we can also use a 2 here. So it means if there is a 1, we can also put a 2 there and calculate for the secondary. So for N2, we are going to use it as N2 is equal to, that will be E2 over what? 4,44 times the frequency times the maximum flux. So we're going to obtain the number of turns on the secondary side, E2 being the voltage that we have on the secondary side. V2, we're going to take that as 480 if you're not given like direct to say this is E. Take that one. Times 4,44 times the frequency. Remember our frequency was, this one is just repeating as it is, 0,0018, like this. So that was going to give us N2, which is, according to this, it was going to give us 1,201 turns to the nearest whole number. Or like I said, to calculate, because you now have N1. You now have N1. So to calculate N2, you could have also used your transformer ratio. V1 over V2 is equal to what? Is equal to N1 over N2, I2 over I1. We need to determine N2 because we have calculated N1. V1 over V2 is already given, this one, the ratio there, V1 over V2. So you're going to take it as 48 over 480 is equal to N1. We calculated N1, remember? We got 110, 120 tens. What is that you want to calculate N2? So you're going to use this, cross multiply this and that. So that was going to be 48. N2 is equal to the product of these two, the 480 and the 120. Whatever that you're going to get there, you divide by 48 since this is a product. So you're going to divide by 48. That's determining the number of tens on the secondary side. And with this calculation, or this one that we are having now, it was going to give us 1,200 tens, a flat number like this. So it's another way. As long you are using your formulas properly, that means you're in the right direction. So that was a part of our transformers there with 10 marks, everything 10 marks as you consider the first part and the second part, which, so you just have to know all these guys, go through your formulas. Then let's check the other part of our question, which is question number 5. Show by means of what? We are given, there we are supposed to show by means of a fully labeled circuit diagram, a single phase resistance, start, induction, run, motor. They need a diagram there. So your diagrams, guys, also do self a favor to work with your diagram. So according to what they wanted, this is our diagram, guys, that we were going to need. Make sure that you name all the components properly. All the components are supposed to be shown. So that's a single phase resistance, start, induction, run, motor. All right. So guys, the diagrams, I do not want to limit you. So use also according to the textbook that you are using, guys. You have your textbook that you are using. Maybe they have this drawn in another way. You know, these diagrams, guys, same as this theory concept. Use according to your textbook. You'll be in the right direction. Then 5.2, what are 5 applications of a universal motor? Where do we like the use? Where we now in on the ground in real life? Where do we use these universal motors? They are used in portable drills, so you can consider the use of the portable drills. You can consider the use of the grinders. All right, you can consider application in grinders, in sewing machines. We also have this in sewing machines. We also have these in vacuum cleaners. In vacuum cleaners, in those food mixers, in blenders. All these, we have the part where the universal motor is used to. If there is any other part that you have, guys, list it in the comment section. We want to learn. We are here to learn, guys. That is the platform for us to learn. So your contribution help someone. What is the name on question number 6? What is the name of the most commonly used component or device that plays the major role in generating electricity at most power stations, regardless of their type? The most commonly used component or device, guys, that's a turbine. Without a turbine, guys, can we get this electricity? No, guys, turbine, we need that. Name 4 sections commonly used for typical electrical reticulation network. The sections that are commonly used, remember there is a generation, a transmission. So these are the sections with a generation. We have the part of the transmission. Remember all these, the part of the transmission. We also have the distribution. That's the distribution. We also have the utilization, part of our utilization. Then on question 6.3, The fig 3 below shows how measuring instruments are connected in an AC circuit using instrument transformers. Now they are saying from that, give the correct name of each labeled part. Write down only the name next to the letters. All right. What is A representing? That is our supply. So there we talk of the supply. Okay. Then with the B, which is our transformer, and this is called the potential transformer. As you can see, guys, this is a indication of what a transformer. Even if you do not know, guys, you can just write transformer like that. Okay, but that's called a potential transformer. That's a potential transformer. Then C here, this part of C is our current transformer, this one. Measuring current, so that's the part of the current transformer. Can also be reminded with what? With A, the ammeter that is represented. Then we also have the part of our D. In this case, the D representing this part. So there are two coils. The D is the current. This one is the current coil. The one that is inner is the current coil, this one. And E being our voltage. There are two coils that, as you can see. So you had to label these parts A to what? A to E. A to E. As we are illustrated there for this question, you're going to get 5 marks and 10 marks for the whole of this question and a total of 100 marks in this question paper. So let's do revise as much as we can. As we can see, our Electrotechnics N4 is not that much. We just need to work with more questions. And as I promised that we are going to work topic by topic very soon. We need to add as much videos as we can as MedZone African motives. We are going to work on that so that every topic you have it as we have where you relate it, so that when you are now answering question papers, you're not going to say, oh, where is this formula coming from? I never had this formula in my textbook. Depending with your textbook, because this will depend also with the textbook that you're going to use. So we are going to have different sources of textbooks that we are going also to refer to so that you can learn as much as you can. So this is what we had, guys, from MedZone African Motives. Till we meet again.